Okay, so the ANOVA function works for GLMs. So if you do ANOVA uh, um, of the fitted model, and this test equals chi-squared, we'll describe that in a minute. It gives you the model, in this case binomial, link is logit, tells you what your response was. And then if you fit multiple models, it sort of just like with linear models, it adds them sequentially. Ideally, you're doing this with nested models. Okay, so the deviance is, so the null model includes just an intercept, and the deviance is the sort of a measure of model fit compared to the previous model. So the degree of freedom equal 1 here corresponds to the one extra parameter we've introduced by including the slope. Okay, so the residual deviance is if subtracted is going to give you the deviance, right? So if you subtract those two numbers, that's going to give you that guy. So that's how you compare deviances, is you take a smaller model and subtract from it a larger model. The difference in the number of parameters is the degrees of freedom, and that quantity then can be compared to a chi-squared distribution with this degrees of freedom. In this case, the chance of getting a chi-squared of 3, 3.5 with 1 degree of freedom, that's pretty far out in the tail. There's only a 6% chance of getting one more extreme. So if I do 3.54 on the standard chi-square table, you get that's about 6%, and then that's about 94%. And you know that this is fairly large for a chi-squared statistic, because chi-squared with 1 degree of freedom is equal to the square of a standard normal. Standard normal, we know that out in the tail, there's about a 5% chance of lying above 2 or below -2, because that's what our confidence interval normal quantile we use is for a 95% confidence interval. And so if you square 2, you get 4, so you know that you knew ahead of time that this number was going to be about 5%. Okay. Okay, so let's just finish by talking a little bit about interpreting odds ratios. So odds ratios are not probabilities, which I think is clear, and odds are of course not probability, but they're a meaningful scale. We're not, we can't actually intuitively think of probability when, there's been lots of studies that show that people misrepresent probabilities, the probability of things in their heads, and they're incoherent, right? They don't think the probability of the opposite of something is 1 minus the probability. So so people have a hard time interpreting probabilities, and they have an equivalently hard time interpreting odds. I do like the one thing about odds in that I like the way it directly relates back to gambling and the sort of example we covered earlier. I think that's actually in the favor of interpreting odds. So an odds ratio, whether you wanted to look at relative odds or relative probabilities, you're going to find the same thing, that a relative amount of 1 implies no difference. So we estimate the model on the log scale. Then if we exponentiate the coefficients, we're looking for 1. If on the log scale, we're looking for whether the coefficients are 0. Right, and that's put right here. And so in our case, we specifically looked for the log odds ratio, but you could also look at the relative probabilities themselves, and that's called a relative risk. And there is it doesn't really satisfy the spirit of a GLM. There is something called relative risk regression, and that's when you want to interpret relative probabilities rather than relative odds. The problem with relative risk, the only problem with it, sometimes people like it better because people want to say there was a 10% increase in probability rather than there was a 10% increase in odds. Personally, I like the odds. But the problem with the relative risk is the log of the relative risk, so the probability is between 0 and 1. So when you log it, right, you get the upper bound is 0, right, and the lower bound is minus infinity. So we don't get the whole range, right? Whereas the logit function converts probabilities to a function on minus infinity to plus infinity. But so this creates boundary issues when trying to fit these models, and that's why relative risk models, in terms of writing the programs, and also when you have probabilities that are close to 1 or close to 0, you wind up with some problems. There's this famous result that says that you can approximate the relative risk with the odds ratio when the probabilities are the small. As Jeff wrote right here, they're not the same, but they can be approximated. And this is done so frequently in, say, the epidemiology literature that people don't even acknowledge that they're doing it. So the other interesting fact about odds, and I'll add this right here. So odds have an interesting use in retrospective studies. And what I mean by retrospective studies, so imagine if you're studying a treatment, or you want to study something like smoking, and you can't follow people prospectively over time. It takes too long. If you wanted to study smoking and lung cancer, you couldn't, say, follow people over 15 years and then determine exactly how much they smoked and then determine who, say, gets lung cancer or not. That's too hard. And a much easier way to to try and look at that would be to go to hospital records and collect get the names of a bunch of people who died from lung cancer and get their information, the age at which they died, and so on. Find some controls, maybe some matched controls, and look backwards. Maybe go contact their family or something, or something like that, to ascertain whether or not they smoked and how much. Or if you're not studying, you could go to live patients and get their smoking history. Would be another kind of study you could execute. In both these cases, what you're doing is you're looking at the outcome as a fixed, non-random quantity. You sample 50 people who have lung cancer, or you sample 50 people who don't have lung cancer. And that number is non-random, but you'd like to treat it as if it was the outcome. Well, there's this interesting fact that you can use the odds to sort of treat that as the outcome, even though it was the designed parameter. And it's a little like flipping x and y in a regression model, like where you've designed at specific values of x and y as your outcome, and you flip it and treat x as the outcome and y as the predictor. And it makes sense that would work, right, in regression, because the slope is really related to the correlation, and the correlation doesn't care which one is the predictor and which one is the response. Of course, the slope does, but the correlation doesn't. So it's a little like that. And it was kind of a big breakthrough in statistics because, for studying, and it did actually come about in the study of lung cancer and smoking. and what's interesting about it is the role that the odds play in those kinds of studies, in that this kind of ability in these binary models to flip the kind of to flip and get the kind of prospective interpretation from a retrospective study, that's uniquely determined by looking at odds. So, at any rate, if you're interested in that, that's not so much a data science topic as it is kind of a core biostatistics topic, but it's a really neat biostatistics topic. It was one of the key people who worked on that and discovered this was a person named Cornfield, who was sort of a famous former faculty from the Department of Biostatistics here, and he also worked at the National Institutes of Health in the U.S. Any rate, so if you want some further resources on this, there's a Wikipedia article on everything these days, but it turns out I find Wikipedia's technical articles actually often quite good. So they have an article on logistic regression, and it's good. The classic textbook on logistic regression is called McCullough and Nelder. Nelder, one of the two authors, both are great statisticians. Nelder, one of the two authors, was one of the authors on the original paper for generalized linear models. Anyway, that's the classic textbook that everyone loves. I was the research assistant for a person named Alan Agresti when I was in grad school, and his book on categorical data analysis I find to be a wonderful treatment of generalized linear models as they apply to categorical data like binary data, Poisson data, multinomial data, and so on. I give you some more links here. Jeff had written this slide, and he mentions I have some lecture notes on OpenCourseWare on Simpson's paradox, which is kind of related to confounding and the impact of confounding on model estimates. Case control studies, which we were just talking about, retrospective case control studies, and the textbook Open Intro has a chapter on logistic regression. All nice resources on logistic regression that you can look at. And I hope after this class you're able at least to fit a logistic regression, interpret the coefficients, and maybe do a confidence interval.